Hi everybody, I am going to explain you about amplitude modulation and demodulation in an analog and digital communications lab. And if you see the trainer kit, the trainer kit contains carrier generator and amplitude modulator, and this one is amplitude demodulator, right? Now let us see the definition of amplitude modulation. The amplitude of the carrier signal varies according to the instantaneous values of the message signal is called amplitude modulation. The amplitude of the carrier signal varies according to the instantaneous values of the message signal is called amplitude modulation. Here the frequency, for example, I am using this function generator to get the message signal, and I am going to take a low frequency message signal which we can call it as modulating signal or baseband signal or message signal. Here I am going to set it less than 2 kHz or in between 900 Hz to 1 kHz. No problem. Okay, that is over. And coming to the carrier signal, I am using another function generator to get the carrier signal. I am setting the frequency of the carrier as 87.64 or whatever it may be. It is in terms of kilohertz, 87 kilohertz. Now let us see. This is the function, CRO, to which I am going to apply. At first I am going to check the input signals. This is the message signal, and this message signal is going to, we can check the output of the message signal. We can check the output of the message signal in the CRO. Now I am taking the output terminals of this function generator and going to connect to this function generator, CRO. Now let us see. Yeah. Right. I am taking channel 1, and this is the channel 1, and output of the function generator to get the message signal. Right. And you can see that here there is the message signal. This is a low frequency signal or baseband signal or modulating signal. Right. That is completed, and we check it. Next, let us check the carrier signal from the second function generator, and here I am connecting to the CRO. Okay, at first we must connect to the ground, right? Later base. Yeah. So this is the carrier signal. Now I am going to apply these two to the AM modulator. Here you can find the AM modulator in the trainer kit. Here this is the AF input, that is a message signal. Message signal is from this function generator. Now I am applying the message signal to the AF input. Now, right, I grounded it. Next, I am taking the second output, which is a carrier signal, and you must ensure that the frequency of the carrier signal must be always greater than the frequency of the message signal. Then we will get the perfect shaped AM. Right. Now I am going to connect the output terminals of the modulator to the function generator, CRO, and from the CRO you can find the amplitude modulated signal. Right. Yeah. Be connected. Right. So initially you may not get directly the AM modulated output, but by tuning the what we call time periods and amplitudes in the circuit. Here you can see that this is a balancing probe, and by varying this probe you can find the variations in the message, what we call AM signal, right? We can balance both the upper sideband and lower sideband in a symmetrical manner, right? So finally we got the AM output. So you can define amplitude modulation as the amplitude of the carrier signal. Here you can see that here this is the carrier signal, and the amplitude of this carrier signal is varied according to the instantaneous values of the message signal. And if you see the envelope of the signal is nothing but the AF signal or message signal. Let us compare the envelope of the AM signal with the message signal. You can see that both are matched. Here I am using here I am using two probes, and I am using two channels. Channel 1 is getting the AM output. Channel 2 is supplied AF signal or message signal. You can see that both are equal. And at the same time, here you can observe different types of modulations, AM modulations, that is perfect modulation, under modulation, and over modulation. You can observe the same. Let us check. You can observe the different amplitude modulations by varying the amplitude of the message signal. Here, this is the function generator which is producing AF signal, and by varying this amplitude, you can see that I am varying the amplitude of the message signal. This is the case of perfect modulation, where V minimum is almost zero. And you can see another modulation, that is over modulation. What happened here? If you see that the upper envelope and lower envelope both are overlapped together, and the lower envelope penetrated through the positive side and the upper envelope penetrated through the negative side, so that the polarities of the V minimum changes. And again you can see another modulation, that is under modulation. This is the under modulation, right? Under modulation. This case is under modulation. This is perfect modulation and over modulation. So these three are the cases we are going to observe in the AM. And if you see the calculations and observations that we are going to take in this experiment is the definition of the modulation index is very important. That is V maximum minus V minimum by V maximum plus V minimum into 100. And here you can see that this is the V maximum. V maximum means, so you can take peak to peak. This one as the V maximum. Here to here it is the V minimum. And for example, in this case, let us measure the V maximum value. Okay, let me set it clearly. Take any reference axis. Here I am taking this line as the reference axis, and here 1, 2, 3, 3.5, almost 3.5 box is there, and here you can see that the scale is indicating 0.2. 0.2 multiplied 3.5. 0. Yeah. So it is almost equal to 0.5, 0.75. Here I am showing to the amplitude modulated signal, which is nearest to the perfect modulation. So let me take under modulation for a clear understanding of V maximum and V minimum. Now there is a loose contact, so that keep it there, right? So this output is showing under modulated signal, or I can say that it is a clear AM signal, and in this you can find the V maximum values and V minimum values clearly. And for example, for the case of V maximum, I am taking this x-axis as a reference. Here to this peak, this is going to give us the V maximum value, and the what we call the value is approximately 2.6. Here 2.6 multiplied 0.1. So it is 2.6 volts. 2.6 volts. That is VM value is 2.6 volts. And let us calculate V minimum value, and it is occupying 0. Here to here. This is here to here. This is the V minimum, and the V minimum is approximately equal to 0.9. Here it is 0.9. So 0.9 V minimum, 0.9. Here V minimum is 0.9. V maximum is 2.6 volts. Actually, I didn't calculate this value. Actually, to calculate what we call modulation index, we require V maximum and V minimum. Now I am taking the ratio, that is 2.6 minus 0.9 by 2.6 plus 0.9 into 100, and the resultant value will be equivalent to the modulation index. And if you want to take the same in terms of percentage, simply you will multiply the ratio. Right? So for this case, let me calculate that. 2.6 minus 9 means 1.7. 1.7 divided by 3.5. And almost it is 1 by 2, which is equivalent to 0.5. So the modulation index is 0.5. In terms of percentage, 0.5 multiplied 100 is nothing but 50%. So in this case, the modulation index value is 0.5, and I already told you that if V minimum and the difference between V minimum and V maximum is very less, then you will get the under modulation. If the difference between V maximum and V minimum is very high, then you will get the perfect modulation. And for the case of over modulation, both the envelopes are overlapped together and polarities of V minimum is going to changes. Then you may get the modulation index value greater than 1. The reason, if you see the formula, the numerator value will be greater than the denominator. Whenever numerator value is greater than denominator, then that ratio is greater than 1. So in this way we are going to calculate the modulation index for different cases of the AM modulation. Let us see the demodulated output. Now the output of the modulator is going to connect to the input terminals of the demodulator. In general, for the case of demodulation, we are going to use envelope detector. So I am going to connect this, and in order to extract the message signal, which is modulated by the AM modulator. And here at the demodulator side, we need to get only the message signal, and we need to cancel the carrier. So to cancel the carrier, we are going to use the what we call envelope detector. So this is all about the demodulated signal. This is the demodulated signal which we supplied as a message signal. Okay, that's it. Thank you very much.